Welcome into our new chapter. Our learning objectives for this video. We want to be able to list our postulates of Dalton's atomic theory. We want to describe matter using our nuclear model of the atom. Let's recall from our previous videos, atoms are the building blocks of our matter. Our atoms here are the smallest identifiable unit of an element. We do have many different types of atoms. They show up on that periodic table of elements. There's about 118 of them. These atoms are used to build up every piece of material in the universe. So you are composed of atoms. And atoms are so incredibly small that there are tons and tons and tons of them in a typical person. 10 to the 27th power of hydrogens and oxygens, 10 to the 26th power of carbons, 10 to the 25th power of nitrogens. There's just an astronomical number of atoms in every living thing. These atoms are coming in and coming out of your body, being exchanged with the environment around you. So actually some fun facts here, about 90% of the atoms in your body are replaced every year on average. And on average, the carbon atoms in your body have been used by 20 other organisms before you. So statistically speaking, approximately 1 billion of the atoms in you right now were probably once part of William Shakespeare, for example. These atoms are so small, but it is possible to visualize them with a handful of techniques. Once again, we have a scanning tunneling microscopy image. Here it is an IBM banner built with atoms, the smallest billboard in the world. Each of these little bumps on the surface is one xenon atom. All right, now that we've been inspired a little bit, let's get to some history. The atomic theory that we know and love was developed in earnest by John Dalton. The idea first materialized in the 5th century BCE by the Greek philosophers, but it wasn't really widely accepted until much later when John Dalton said, "Oh, this is how things probably are," in 1808. The idea from the Greek philosophers and eventually from John Dalton is that if you cut something in half, it gets smaller. If you cut that thing in half again, it's even smaller. If you keep cutting your material in half, at some point, you might get to the smallest little unit of that material, which the Greeks were calling atoms, which means cannot be cut. John Dalton expanded on this and came up with his atomic theory outlined by these 4 postulates. Number 1, every element is composed of atoms. These atoms cannot be created or destroyed. Number 2, atoms of the same element should be identical to each other. Atoms of different elements are different from other elements. That is to say, 2 carbon atoms should be identical, but a carbon atom and a silver atom are different from each other. We have now found about 118 unique atoms, 118 unique elements. Number 3, you can combine your atoms to build more complex structures called molecules. Think about your atoms like Lego pieces or building blocks. You can combine them together following a set of instructions to build a certain molecule. And lastly, number 4, atoms are not going to be changed from one element to another. All they get to do is rearrange into different structures. The building blocks are what we have, but if we have this pile of building blocks, you can combine together in a number of different ways. We call this chemical reactions, when you take apart the pieces of one molecule, rearrange them to build a different molecule. But again, we're not creating or destroying our pieces. All we get to do is rearrange them. There we go. This is John Dalton's atomic theory, a tremendous step forward in terms of scientific ideas. This is not perfect, and actually in just one slide, we're going to improve upon John Dalton's atomic theory. But in terms of the way we think about the universe, this is an incredible, incredible leap forward. All right, now that we have our basics, we can improve. As it turns out, our atoms are not the smallest thing in the universe. There are subatomic particles, things that are smaller than atoms. And the first that was discovered was the electron. J.J. Thomson did a famous experiment with cathode rays, which saw that you could take your atom and eject little negative pieces from it. That means there is a negative piece of our atom that's able to fall off. We call those electrons. And there has to be some positive part of our atom that's left behind. Thomson's proposal for how our atoms actually looked was this plum pudding model. You can think about it like a blueberry muffin here, where we have our negative electrons, these little blueberries or plums in our muffin, and we have our positive part, which is all of the cakey, doughy part of our muffin. To test this theory, Ernest Rutherford, who was working with J.J. Thomson for a while, did an experiment known as the gold foil experiment. Here, Rutherford took a very, very thin piece of gold metal, hammered down to be only a few atoms thick, and he shot alpha particles at that gold foil. The idea was, if this plum pudding model was correct, then our alpha particles being shot at that gold foil should travel right through, because our positive and negative charges are so dispersed, there's nothing really to get in the way. Picture this like going to a shooting range and shooting bullets at a piece of paper. These bullets should punch right through that paper, and they should all go and hit our detector on the other side. Interestingly, this is not what happened. Some of our particles, some of our bullets hitting that paper did not punch right through that paper. Some of them bounced off even at really sharp angles. Imagine if you were at a gun shooting range and every 1 out of 1,000 times that you shot at a piece of paper, that bullet bounced back right at you. That would be incredibly surprising. What that tells us is that our plum pudding model can't be correct. We need to come up with something better. Our better theory of the model is called the nuclear theory of our atom. Here is our atom. Instead of being shaped like a muffin or a plum pudding, this atom is almost entirely empty space with just a teeny tiny area in the center that contains our positive charge. Our positive charge is not like the doughy part of our muffin. Instead, it's this teeny tiny little pellet that exists in the middle, and we're going to call that the nucleus. This nucleus contains all of our positive charges, and it contains all of the mass in our atom. The rest of the atom gets to be almost entirely empty space with our electrons, those little negative pieces, floating around in that empty space. So there we go. Our better picture of the atom has our electrons occupying the volume of our atom, but containing almost no mass. The nucleus in the center contains what we call protons, positively charged particles that exist in the tiny, tiny, tiny area in the center of our atom. And, one additional thing, we also get to have neutrons in our nucleus. These are neutral particles that are heavy but do not have a charge. More about these in a moment. This model better predicts the results of our gold foil experiment. In the plum pudding model, things should pass all the way through our gold foil, which we do see a lot of, but that plum pudding model does not predict any of these deflections. Whereas our nuclear model of the atom says, okay, most of our particles will pass right through, but every once in a while you might hit that nucleus, collide, and bounce off, which will result in some of these little deflections, like a bullet bouncing off your piece of paper if you happen to hit the very center of that atom. How often these particles bounce off the nucleus can give you an estimate for the size of that nucleus. As it turns out, the size of that nucleus is so small compared to the size of the atom, it would be as if it was a blueberry sitting inside of a football stadium, where the blueberry could be the nucleus and the entire football stadium would be the size of the atom. These deflections do not happen very often, but they do happen, which means we must have this nuclear model instead of something like the plum pudding model. Okay, let's get into some of the details of our subatomic particles. We said we have protons, we have neutrons, and we have electrons. I'm going to use the symbols P, N, and E minus to denote these. Let's start by talking about the mass of our particles. Protons and neutrons are relatively heavy. Our SI unit for mass is kilogram, as we recall, but thinking about a proton or a neutron or electron in terms of kilograms doesn't make a ton of sense. So instead, we can introduce this new unit, AMU. This is called the atomic mass unit. In this type of unit, our proton is approximately 1 atomic mass unit. Our neutron is approximately 1 atomic mass unit. And our electrons are 0.0005 atomic mass units. This is why the nucleus contains all of the mass in our atom. Protons and neutrons are orders of magnitude heavier than our electrons. Because of this, we can mostly ignore the mass of our electrons. It's not actually 0, but we can round down to 0 because it's not going to really affect the total mass. Our picture here, if you're thinking about protons and neutrons as the size of a baseball, our electrons would be about the mass of a grain of rice. If you're adding up something like a carbon atom, which has 6 protons, 6 neutrons, and 6 electrons, we have 12 atomic mass units from our protons and neutrons. But our electrons, we're adding 6 grains of rice to about 12 baseballs. Is that really going to meaningfully change our mass? The answer is not really. We can define something called the mass number as the number of heavy particles in our atom. This is going to be the sum of protons and neutrons. Since electrons are much smaller, we can ignore them in terms of mass. Secondly, we can talk about the charge of our particles. Protons have a charge of +1. Electrons have a charge of -1. Our neutrons are neutral, which means they have a charge of 0. We don't have units written down here. Once again, the SI units are not very convenient. The charge of a proton or electron is positive or negative 1.6 times 10 to the negative 19th coulombs. We're not going to use this teeny tiny number. Instead, we can have things as either +1 or -1. This is going to be our relative charge. Some notes about our charge. Our charges add up together or cancel out together. If you have a positive charge and a negative charge, the result is going to be something that is neutral. Likewise, if you have 2 positive charges and 2 negative charges, our result here will also be neutral. More intuition about how our charges behave. If you have 2 positive charges, like charges repel each other. Think about magnets trying to go the wrong way. It's going to be hard to push 2 of the same charge together. Same thing if you have 2 negative charges. Alternatively, if you have opposites, opposite charges will attract. Just like in the sitcoms and the rom-coms in media, opposites are going to attract. A positive and a negative will stick together. We can introduce a formula here if you want to calculate the total charge. We can add up all of our individual charges. All of your positive charges increase the charge. All of your negative charges decrease the charge. This is exactly the math we were doing over here. 2 plus combined with 2 minus adds up to 0. We have some examples of some math problems that we might see. I've written up our formulas up at the top. If you want to calculate the mass, those are our protons and neutrons. If you want to calculate the charge, those are our protons and electrons. The question here, what is the charge and mass of each of these atoms? We're looking for something with 12 AMUs and charge neutral. Neutral charge is 0. Our first atom has a mass of 6 plus 3, which is 9. It has a charge of 6 minus 6, 0. Is this the atom that we're looking for? Well, no. Our second atom has a mass of 3 plus 3, 6. And it has a charge of 3 minus 6, -3. Again, is this the atom that we're looking for? Well, again, no. Our third atom is a mass of 6 plus 6. We have a mass of 12. And our charge is 6 minus 6. Our charge is 0. Is this the atom that we're looking for? Oh, yes, it is. But for fun, we can check our last atom as well. We have a mass of 12 plus 0. And a charge of -12. So there we go. Only one atom of these 4 fits the criteria that we are looking for. There we go. We've learned about our Dalton's atomic theory, and we can list out those postulates. And we can describe our matter using this nuclear model of the atom, the type, location, and properties for our protons, neutrons, and electrons. Well, there we go. Thanks so much for tuning in. Hope you all have a great day, and I will catch you next time.